Hello and welcome to lesson 30, where we are officially starting curve sketching. So you've seen different characteristics of graphs. So we looked at critical points, asymptotes, and points of inflections, as well as the first and second derivative tests. And now we're going to put all of that information together and start sketching graphs. So throughout the next lessons, you're going to see polynomials, rational functions, as well as some special functions, so our trigonometric, exponential, and logarithmic functions. And we're going to be using a curve sketching algorithm. So today's focus is just polynomial functions, so it is a little bit shorter of a lesson. I'm going to introduce the algorithm to you. We're going to get a few practice questions, but the practice itself, the practice sets will take you a bit longer. So as you're going to see, there are 10 steps to this, and I know it sounds a lot at first, but it's just all the different things that we have to consider for our graphs. And it's stuff we've been already doing, but doing it all together takes a bit of time. So that's why I wanted to give you more time to actually do the practice sets. And as always with especially polynomial functions or any of these next functions, you can always graph them using graphing tools to check your answer or check your sketch of your curve in comparison to the exact curve. So let's look at the algorithm first. So with any given function, you first want to consider the domain. And I guess from there, you also get the range. But because domain is our independent variable, we for sure want to consider the domain. Based on that, we also will find any discontinuities or limitations. So for example, like asymptotes that we saw, or values of x that we need to be cautious about with our function. And with polynomial functions, you're not really going to see that, but when we get to the rational functions, you will have discontinuities there. It also could be just that the domain, the way it's defined to you, for example, for a polynomial function, if you're explicitly told x cannot be 1, then you have to analyze that and interpret that as well. And for polynomial functions, it could be like a whole, or if you have a piecewise function, you might have jump discontinuity. So definitely consider your domain. Now, once you have any discontinuities, we want to investigate the function's behavior on either side. And in relation to that, it's also we're checking if it's a vertical asymptote. So if we're approaching infinity or negative infinity, then we have a vertical asymptote. Or if it's a hole, we are approximating where that hole could be based on the output. Next, we want to find our intercepts. So this is a little bit of a new addition that we didn't see in prior lessons, because now we really want to get a more exact sketch of our curve. So we find the x-intercepts and y-intercepts. This one should be plural. And this is going to help us, again, get a more accurate curve. Next, we find the critical points. So one step in there, we have to find the first derivative, and based on that, we find the critical point, so where the first derivative is equal to 0. And we apply the first derivative test to determine whether the critical point is a maximum, minimum, or neither. And if it's neither, we have to do further investigation, which we have already seen how we could, for example, do that with second derivative test or the sign chart. Next, we want to find any horizontal asymptote. So we're determining the end behavior of the function. So as x is approaching positive or negative infinity, and if there is a horizontal asymptote, where that is located. Next, we have the second derivative. So we first find what the second derivative is, and based on that, we can apply the second derivative test to determine possible points of inflections. And if we find the intervals of concavity here as well, then we can confirm those points of inflection as well. And finally, we check oblique asymptotes as well. So again, this is not for our polynomial functions, but in our next lesson where we see rational functions, we definitely want to be checking for oblique asymptotes. And remember, oblique asymptotes happen when the degree of the numerator is exactly 1 more than the degree of the denominator. And finally, we are going to be sketching our graph. So a few things here. As you are doing these steps, so for example, if you find a vertical asymptote and then you find the intercepts, you're going to be plotting those right away. So have your graphing paper next to you and start by adding your dashed line for the vertical asymptote. When you have the x-intercept, start adding those points. When you have a horizontal asymptote, again, draw your dashed line. And finally, when we do the sketch at the end, it is mainly for our function itself, where we are connecting some of those points based on concavity and points of inflection, and then that's our final function. And some things here as well, use information that you already know. If you have a quadratic function, use what you know about quadratic functions. So not all of this is going to be necessary because, for example, you can tell when a quadratic is concave up or down based on the value of a. You can also, for example, curves of x cubed, you also have an approximate idea of what that looks like. So that's really going to help you visualize it a little better. Finally, I want to emphasize that we're using approximate points here. So you'll see, for example, when we get a square root or a rational expression somewhere, we approximate that to usually 2 degree or 2 decimal places because we're focusing on the shape rather than accuracy. If we wanted accuracy, we have graphing tools for that, but this is a opportunity to analyze the characteristics of functions based on all the information you've learned so far and use this to draw approximate shapes. Or again, if you don't have graphing tools available to you, how would you approximate the shape of a given function? So let's look at our first example, and it's a basic one, but I wanted to show you with a graph that you already know what it looks like, how all of this information would look. And just as a reminder, we already know this is like similar to the quadratic function, but it's a little bit more something like that. Again, approximate shape, not exact. So um, based on this, and yes, exactly, it resembles the quadratic function, and it should look like this, and especially because it's positive there. So first, f prime of x is 4x cubed, and the second derivative is 12x squared. And I hope already you see that sometimes you're also going out of order with these. Like, it's not, the algorithm is pretty much telling you a general guide. But for example, yeah, you can always start with finding your first and second derivative at the beginning and then start using it for when you need it. So now, applying the second derivative test here, I want to find, and sorry, one more information I'm going to add there. I pretty much also have checked for domain discontinuities, again, because I just know it's a polynomial function, so it is defined on all values of x in the real numbers. It doesn't have any discontinuities, and based on that, it also doesn't have any vertical asymptotes. And so then we also know that x and y intercept is at 0, 0, and so that's why I'm already at the first derivative test and the critical points. So and as well as the second derivative and the second derivative test. So applying the second derivative test, we know that we want to find where f double prime of x is equal to 0. And this happens when x is equal to 0. So this information is not does not tell us right away if we have, for example, a local maximum, a minimum, or a point of inflection. It is a possible candidate for a point of inflection, but we need further information. So we also test the first derivative test. So the first derivative test tells us that f prime of 0 is also equal to 0, which means we have a critical point, but again, it's not enough to determine the nature of the point. So that's why we have our sign chart here set up. So this is x is 0, and one thing I'll point out here, you can have this graph, oh, this should be x is greater than 0, sorry. This could have just been 2 sections where this is x is less than 0 and this is x is greater than 0. And this line in the middle is x is 0 itself. And notice here how I have a question mark because we're not sure yet if it's a point of inflection. But as I fill this up, so I can tell the first derivative goes from negative to positive. So from decreasing to increasing. So I can tell it is a minimum here from this information. And I confirm that from here because it is concave up and concave up, then it's not a point of inflection. It is just a local minimum here and the concavity is not changing. And again, we already know what the shape looks like, but you can also have a sketch of the intervals. So here I know it is decreasing in concave up, so it would look like this. And on this part, it is increasing and concave up, so it will look like this. And of course, putting those together, we get our shape, which is like that. Now, here, just putting that information in words, since the second derivative is greater than 0 on either side of x is 0, so then the concavity is not changing. It is not a point of inflection, but there is a change in sign, which tells us that it is an absolute minimum, which is what we were expecting. Now we can graph this. So for I know I already went through all the information, but again, you could have been plotting those as is. So I would have had this point right there, which is my x-intercept, y-intercept, critical point, local minimum, all of the above. And um, depending on the function, when it is something as simple as f of x is x to the power 4, you could approximate some values here. So have 1, or maybe let me spread it out a little bit more. 1, 2, 3, and then here we would have -1, 2, -3, and then perhaps here I would choose 2, 4. And remember, you pick your scale, right? So based on the function, you pick a scale that you think is best. So here I know that I would have this point and this point if I need the output of the function. And 2 would be, oh, so I already don't even have this approximately here. And approximately here. And so if I'm sketching this now, I'm just connecting all of these points. Okay, something like that. But again, because this is a sketch, even if you had just had something like this, you just show me 0, 0, and then draw this shape. Oh, maybe just draw it a little nicer. You draw this. This is fine for curve sketching because again, it's approximate, not exact. Now let's look at our second and also last example because again, I want to give you more time to practice on your own. So here we have -3x cubed minus 2x squared plus 5x. This is a polynomial function. The domain is x in all real numbers, so there are no discontinuities or asymptotes. So now I am actually following more of this algorithm here, step by step. So I've already done the first analysis there. Now we find the x-intercept. So I'm doing this just by factoring. So they all have an x in common, so factoring that out. And then this is my quadratic function. So I'm just factoring using decomposition here. So I know -2x is 3x minus 5x. And use any factoring method that you feel comfortable with. I'm just showing you a different method here. And so factoring these two out, I can have that x minus 1. So I can factor x minus 1, and I'm left with -3x minus 5, which is equal to 0. So now I have three x-intercepts, which occur at 0, 0, 1, 0 from here, and -5/3 and 0. And of course, my y-intercept is going to be when x is 0. So when x is 0, all of these are 0. So my y-intercept is 0, 0, which was already there. Now we find the first derivative. So we are using derivative rules here. So we have -9x squared minus 4x plus 5. And we want to find the critical point. So what values of x is this equal to 0? And again, this is a quadratic, so I'm just factoring here. And again, I use the decomposition method here. So if you factor, you get -9x plus 5 and x plus 1. And this is equal to 0 when x is -1 and when x is 5/9. So I will first apply the first derivative test. So for example, we choose x is -2, which is less than -1, and we see that the first derivative is negative. Then we choose an x is 0, which is between -1 and 5/9. And always try to use friendly numbers whenever you have them. This is a friendly number we can use. And the first derivative here is positive. And in my final interval, x is greater than 1, or sorry, x is greater than 5/9, I pick 1. And so f prime of 1 is negative here. So because the derivative is here is negative, so we have decreasing increasing and decreasing. And so because we change from decreasing to increasing here, so the derivative changes from negative to positive, then -1, -4, which is just the point, I'm finding the points from here. This is -1, -4. And now this one is when we start approximating. So I will write the point as 0.6 and 1.6. Then this point is a minimum because, again, we're going from negative to positive. And in the second one, we're going from positive to negative, so from increasing to decreasing. So this is a maximum. Furthermore, we also have our now intervals of increase and decrease based on this information. Now, since this is a polynomial function, we also know that the behavior as x is approaching infinity, and we can clearly see from the function here. So as these x values are increasing, or you could even, just to show you what we did when we did our lesson, if I factor out x cubed here, then I have -3 minus 2x plus 5 x squared. And clearly these are going towards 0, and then this is just a constant here, but this is the part that we care about the most, and x cubed goes towards infinity. That's just the property of a polynomial function. So then same with here. We say that it is going towards positive infinity. That being said though, remember it is x cubed, and this is why it's important to use information you already know about graphs. You know that the curve looks like this. So as we are going towards positive infinity, we are also going towards positive infinity here. But as we go towards negative infinity, we are going towards negative infinity as well. So that's this. Oh, that being said, because here it is a negative, we do have to consider the negative is an important part. You need to factor that part out. So this is negative x3, and then 3 plus 2 over x. Okay, so the constant doesn't matter as much, but the negative matters because now consider the negative of this would be, oh, oh no. It would look like this. So as we are going towards negative infinity, this is going towards positive infinity. And as we're going towards positive infinity, this is going towards negative infinity. And that's exactly what we have here. Now we find the second derivative to see if we have any points of inflection. And I would expect there, based on just what I know from cubic functions, for there to be a point of inflection. So from the first derivative, we find the second derivative, so -18x minus 4. And now we want to find values of x for which the second derivative is equal to 0 to find possible points of inflection. So this second derivative is equal to 0 when x is -2/9. And so this one I've approximated here. And if you check the concavity, this would be a point of inflection because, again, because first what we know about the about cubic functions, but if you check f double prime, for example, let's do -1, and then 0. So when this is so let me So when we check this one, 0, so this is just -4, which is less than 0, so concave down. And when we have -1, then we have greater than 0, so concave up. So because we have a change in concavity, then this is a point of inflection. And again, we have an approximate value here. And that's exactly what I'm seeing here as well. This is concave up, which is the values before. Well, in this one, because it's for x cubed, it's a little bit different because it's at this point, but values before or less than -2/9 are going to be concave up, and values of x greater than -2/9 are going to be concave down. And also, I mean, we already did check this based on the first derivative test, but how can you use the second derivative to confirm these points are minimum and maximum? So remember, we find -1. This is 0. So that's actually what I had done. Coincidentally, we picked the same point. And if you check this one, so this being concave up means it is a minimum, or let me just write min. And this being concave down means that we have a maximum. And this is based on second derivative test. Oh, and that's actually what we had right there. Now we have enough information to sketch the graph. So I am going to go back a little and do this step by step. So starting with my x-intercept, so 0, 1, and this one we can approximate here as well. So we can do negative 1.67. Oh, it's a point there. Okay, so going back here now, we certainly have this 0, 0 point. So I will need a little bit of scale here. So perhaps let me do 1, 2, or wait, you know what I'm going to do? I'm going to do 3s. And the reason I do that is because now I can actually say that that one is -5/3. We have, or hold on. I'm going to do all of these in black. So I can draw my graph in blue. Okay, so this is my first point. This is -5/3, and then 1. Now we have also 5/9, which is approximately here. And so we have the x-intercept, y-intercepts. Okay, we know we need the minimum and maximum. So we also have this one here. Oh, and I think I actually found those 2 points. So there we go. -1, -4. So if I continue -1, so then we have -1, -4 there. And then the other one was 0.6, 1.6. So I hope you can see this does take a little bit of time to like analyze everything, choose your scales, check everything, and you really want to be accurate with these. So double checking is very important. Okay, there. So I actually don't even need these because I had my points. Okay, so now I also know this is a max and this one is a minimum. And also we need this point here as well, our concavity. So -0.2, -1.2. So maybe somewhere here, approximately. Okay, so then we know that all of these are going to be concave up. So I'm going to start connecting this concave up. And then now we're going to go concave down. Oh. Okay, there we go. And that is a sketch of our curve based on all of that information. So again, double check. We have our 3 x-intercepts, we have our y-intercept, we have our maximum, our minimum. This one, it's hard, it's a little bit harder with these ones, but there is a point of inflection, especially when you put the point there, you are acknowledging it. And of course, we have this is going towards um, positive infinity as expected. And as we are approaching infinity, we are going towards negative infinity also as expected. And that is our last example. So you have lots of different curves to sketch and get practice with, and of course, verify your solutions using graphing technology. And as always, if you have any questions, don't hesitate to reach out. And I'll see you all next class to do more curve sketching of rational functions.